Hello everyone, welcome back to chapter 6. Today we're going to be working on section 6.2, which we're still talking about the normal distribution for chapter 6, and today we're going to talk about applications of the normal distribution. And we're going to try to fit 6.3 on this video also. We'll see how long things go. So for the learning objectives for section 6.2, we want to learn to find the area under the standard normal distribution given various z-values. Now we really actually already did that in section 6.1, but we're going to continue doing that. Also find the probabilities for a normally distributed variable by transforming it into a standard normal variable. So in the last section, we were given the z-values and then we used those to go to the chart and find our information. In this section, we're going to be given the x, and we're going to have to use our z formula to then convert that x value that we're going to be given. So we're going to be given this x, and we're going to also be given the mean and the standard deviation, and we're going to plug that into the formula to get our z before we go to the chart. And then also find specific data values for given percentages. That's the ones where we work backwards, where we are given the percentage and then we have to go to the body of the chart and go out to find the z-values. That's something that's going to be on the homework, but I won't put that on the exam. So, and again, and the biggest thing here is we're going to be working on applications. So in the last section, we were just given the values. We weren't really given any specific scenarios around it, except I did make up the scenario of the test scores. We had like an average of 72, mean of 72 with a standard deviation of 10. And I kind of put that in there to kind of give us more of a feel for what we were doing, but we didn't really have any actual like real life application type problems in section 6.1. All right, so now they're going to talk to us about how to find the area or probability under a normal distribution curve. We have to standardize the values. So standardizing the values is where, again, like in this scenario here, it says, suppose the amount of blood is normally distributed with a mean of 5.2 and a standard deviation of 0.3. And we want to know the percentage of people that have less than 5.4 liters of blood in their body. So what we're saying by doing this calculation with finding the z, we're finding, instead of knowing that the mean is at 5.2 and trying to figure out how much above average this is, like in this case 5.4 is above 5.2, we want to know how many standard deviations we are above. So in order to find how many standard deviations we are above that average, we have to take these numbers and plug them into our formula. So z, again, is x minus mu over sigma. So if we look through the problem, it says suppose the amount of blood in the human body is normally distributed with a mean of 5.2, so that's going to be our mu, and a standard deviation of 0.3, so that's going to be our sigma. And we want to know what percentage of people have less than 5.4. So that's going to be our x is going to be 5.4. We're going to put that in, 5.4 minus 5.2 divided by 0.3. And that's going to give us 0.2 over 0.3, which is the same as 2/3. So that comes out to be approximately 0.67. So that's what we're going to use for our z value when we go to the chart. We're going to use z of 0.67. Now we can use the exact same techniques that we used in the last section, and let's refresh our memory on those. So remember, if it is less than, then we can just go to the chart, because that's what the chart is built for. It has all the values for the percentage that you're at a z-value or below. Percentage or probability or the area, they all, again, essentially mean the same thing. Then if they ask for more than a certain value, then we have to take 1 minus the chart, because the chart, again, gives us to the left of a value, and if we need to the right of a value, then that together, the below and the above, should add up to 1. So if we can calculate, we can find out from the chart what's here, but then we have to subtract that from 1 to get what we really want, which is up here. Okay, and then the third thing is if we have between two values, then you have to find two different chart values. We've been calling them chart 2 and chart 1. And chart 2 will be the larger one, chart 1 will be the smaller one. Again, if you calculate them the opposite way, you'll realize you have that because you need to take the larger minus the smaller because we need a positive value. So we find both the chart values and we subtract them, and that'll give us the area between the two values. Because again, we're going to have our first value, so our Z2, and then we're going to have our second value, we'll call that our Z1, and if we want to know in between those values, then we have to take Z2, which is all the way down, and subtract off Z1, which is just from here down, so that we can get the in between. So with that said, let's look at this one. So this one says we want to know what percentage of people have less than 5.4. Okay, so this is a type 1 here. This is less than. So we need to look on the chart for the value that is less than Z equals 0.67. Okay, so we're on our chart, which by the chart we mean the standard normal distribution, the Z chart. And we're going to go, this is all the negative Z values, so we've got to go to the second page. And remember that it tells us here that the chart gives us from a Z value down, which is what we want in this case. So we're going to look for 0.67. So 0.6 is here. 7 would be this column. And so now we should be able to draw from, if we come down from the 0.07 and over from the 0.6, we get 0.7486. Okay, so that's our value. We're saying that from a Z of 0.67, let me try to make that curve a little bit better. Okay, so from a Z of 0.67 down, that is 0.7486 of the chart. So the probability that a adult has a volume of 5.4 liters of blood or less in their body is the same as the probability that we're under 0.67, which came out to be 0.7486. So this is exactly like what we did before. It's just we have one extra step in that we have to calculate our Z value first because they're not going to give us the Z value. We have to standardize it ourselves and change the 5.4 liters to 0.67 standard deviations. All right, so let's look at another problem. So for example B, it says data says an average American household generates an average of 28 pounds of recyclable paper each month. So we've got, I always like to draw a picture for those. If you get in that habit, I think that'd be a very good habit to get into. So it says the average is 28, and they want to know, and it's normally distributed, so 28 is our mean. It's normally distributed with a standard deviation of 2 pounds, so this is our sigma. What is the probability that a randomly selected household generates more than 30.2 pounds? So I'm going to draw that right away. So we're up here above the 28 at 30.2, and we want to know the probability that we're above that. Now, I can't use 32.2. That's not going to be on the chart. The chart has the values standardized. So I have to figure out how many standard deviations above average 30.2 is. So I have to standardize it by finding its z value. So I'm at 30.2. My mean is 28. And we're going to divide that by the standard deviation of 2. Hold on, let me go back. I want to write the formula down before we write the numbers in. So remember that the formula is x minus mu over sigma. So in this case, our x is 30.2, our mu is 28, our sigma is 2. And so we get 2.2 over 2, which comes out to be 1.1. So we're going to look on the chart, and we're on the second type because it's to the right, because it's above, we're going to use 1 minus the chart. So we're going to look this up on the chart, and then we're going to take 1 minus that value. So let's get rid of this. We were at, what was it, 1.1. So here is 1.1, and then you might say to yourself, well, there's not a hundredths place, or yeah, a hundredths place, so where do I go? Well, 1.10. So we're going to come across to just 0 and then down, and we're going to end up at 0.8643. Now remember, that's this way. So from here down, change colors here. So from here down, we just found out that was 0.8643. But we don't want from here down, we want the other side of that from here up. So in order to get that, we're going to take 1 minus that 0.8643, and that'll tell us that above that is the remaining, so we have about 86% that's below. We're going to have a little bit less than 80 or than 14% that's above. So 0.1357 or 13.57% if we're talking about the probability. So the probability that you select a random family and they have over 32.2 pounds of waste paper in a month is 13.57%. Okay, so now we've done, this is one where we did below. So we had a value, we computed the z as 0.67 and it wanted below that, less than. Now we've done an above, and you guys know textbooks well enough to know the next one's probably going to be a between. But we did the first type where we just went on the chart. Now we did one where they wanted to the right, so we did 1 minus the chart, and now we're going to do one that's between. So using the same data, what is the probability that a randomly selected household is generating between 27 and 31? So in this case, our x2 is 31 and our x1 is 27. And we need to go, because we're doing a between, we need to calculate 2 z values, find both of those on the chart, and subtract them. So this is our third type. If it's between, we go to chart 2, and we subtract chart 1. We find 2 values on the chart and we subtract them. So in this case, our first z value, or actually we'll call this our second z value, is 31 minus our average, which was 28. We have our same average we had before. We still have mu of 28, and we still have sigma of 2, because it said to use the same data from the last problem. So we have 31 minus 28 over 2. And again, if you want to put that down. Let's put the formula down before we write it in. So we had mu of 28, sigma of 2, and our formula is x minus mu over sigma in order to standardize it. So our x is our 31 right here. Our mu is 28, and our sigma is 2, and that gets us 3 over 2, which is 1.5. And then we need to do that for the other value, for the x1, to get our z1. And we're going to get, this was our x2, so now we're going to do x1 minus mu over sigma. And in this case, our x1 is 27 minus 28 all over 2. That's below average, so we have a negative 1 over 2, which gets us negative 0.5. And be really careful when you go to the chart. You have to make sure that you're on the negative side, that you don't get 0.5 instead of negative 0.5. So we're going to pull those values off the chart and see what we get. So our first one was 1.5. 1.5, again, this is a 1.50. And 1.50 gets us 0.9332. So that's our first value. And then our other value was a negative 0.5. Go up here, make sure we're on the first page. And we've got negative 0.5. And again, this one does not have a hundredths place, so it's just going to be negative 0.50. So we're going to come down the chart until we get to where they cross each other, and we get 0.3085. So we're now going to take our 0.9332 and we're going to subtract our 0.3085, and the in-between percentage or area, the area is 0.6247. The probability that you're within that region is 62.47%. Most of the time Alex just asks for this first number. I just, again, like to do the percentage because I think that makes sense in some people's brain a little bit more. But Alex is going to have you put the 0.6247. Okay, so now we've done all three types. And the only difference, again, between these and what we did in 6.1 is in 6.1 you were just handed the z-values. The z-values were given to you. Here they gave us the x values and we had to compute our own z-values. So there was one extra step before we went to the chart. But once we went to the chart, there were still the three possibilities. If it was below, we just went to the chart. If it was above, we did 1 minus the chart. And if it was between, we did chart 1 minus chart 2. Less than, go to the chart. More, 1 minus chart. Between, chart 2 minus chart 1. Okay, so let's look at the last type that they're going to be talking about as far as the examples is the ones that I said I'm not going to put it on the exam, but there will be some on your homework, where they give us a specific probability and we have to go to the body of the chart and work our way out to find the z-value. So it says to qualify for a NASA Space Academy, candidates must score in the top 10%. So top 10% of the test. Assume that the test scores are normally distributed with a mean of 200. So that's our mu. Standard deviation of 20. That's going to be our sigma. What is the lowest qualifying score? So we're going to go to the chart and we're going to figure out the z value for that qualifying score, and then we'll have to convert it. Okay? So when we think of what information they've given us, what we need to know, again, we're working backwards, so we know the percentage before we know anything else. We know that 200 is in the middle, but we've got to be The candidate needs to be in this top 10%. The only problem with this is the chart doesn't give us the top of anything. It doesn't give us the upper, it gives us the lower. So if you're in the top 10%, that means you're in the upper, you're above 90%. And the chart is going to give us this red area. And we're going to need to find the 90% on the chart. So when we go to the chart, we're not going to look up 0.10, we're going to look up 0.90. Again, there's different ways to do this because the chart is all symmetric, but I like to stick with just one method. So we'll use this method. Okay, so we're going to go to the body of the chart, and we're going to look in the body of the chart, meaning the inside part, for 90%. 0.9000, or as close to it as we can possibly get. So we see, I see 0.8997 right here, and I see 0.9015. Which of those is closer? Well, they're both fairly close, but this is only 0.0003 below, whereas this is 0.0015 above. So this one is closer to the 0.9000 that we're looking for. So we're looking for 90%. This is the closest value we can find. So we're going to bring that across and up, and that's going to give us our z-value. So our z-value is 1.28. That's the closest we can get, 1.28. So we know now that our z-value is 1.28. But that doesn't give us our score. We need to know the score. So, hate to tell you, not to traumatize anybody, but we got to go back and do a little bit of algebra solving. Okay, we got to plug this into the formula and solve it. So our formula, remember, is z equals x minus mu over sigma. Well, we know z is 1.28. We have the answer already. We're trying to find the x. We don't know x. We're trying to find that. That'll be the score that you have to get at least that score or above to be considered for the academy. The mean is 200. And the sigma is 20. We had those up here, remember. Mu was 200, sigma was 20. So when you're solving these, in order to get the 20 off the bottom, we're going to want to take both sides times 20. That will cancel these. That gets us 25.6 over on the left side. And then on the right side, we just have x minus 200. And so now all we have to do is add 200. What this 25.6 is telling us is that the candidate needs to score 25.6 points above average. Well, average is 200, so let's add that on, and it'll give us our score. So our score is they have to score 225.6 in order to be considered for the academy. So 225.6 is our score. Now, these are probably not decimal scores, so in all likelihood, we would say that they have to score 226 or above. Because it's probably not a rounded value, it's probably all whole numbers. So 226 or above is what they have to score in order to be in that top 10% and be considered for the academy. We have one more that's similar to this, and we can't find just two random bounded areas. It has to be either like in the last section where it's from zero, like from the middle over, or it has to be symmetric. So in this case, we're doing one where it is symmetric. So you've got one here and you've got one here, but they're both the same distance away. It says systolic blood pressure for adults is normally distributed with a mean of 120 and a standard deviation of 15. A researcher wants to find the limits for the middle 60% of the population. So wants it centered around the average. That means that when we draw this, I highly recommend when something's not making a lot of sense with these normal curves to draw everything you can. We know 120 is in the middle, and we know that between here and here, we want that to be, we want that to be 60%. Well, what does that leave us? We don't need the middle 60%. We need to know where would that be as far as on the chart. We need a value, a specific value to look up that much and below. So if we have 60% in the middle, that leaves us with 40%, but it has to be split between the two sides. So that means to the left here, we have 20%, and to the right here, we have 20%. So we actually have a choice as to what we'll look up. I'm going to use the left-hand one. So if below here is 20%, that means that I'm looking for this z-value. And that means I want a z-value of 20%. So I'm going to look in the body of the chart for 20%. All right, so I'm going to search through this chart. I know it's going to be below 0 because it's going to be below average. So I'm looking for 20%, as close as I can get to that. Let's see, I've got 0.2033, 0.2055, and 0.1977. Well, in this case, the 2005 is only 0.005 above, whereas the 0.1977 is 0.23 below. So in this case, the one that's a little bit above is the one that's closer. Okay, so that's our value. That's going to give us our z. We only have to look up one of these, and I'll show you why here when we get this answer. So we're going to go from the 2005, bring that over and up. Scroll this up a little bit. 0.4. Can't quite, here, let me minimize it so we can see it all at once. There we go. Okay, so we've got negative 0.84 is our z-value. So our z-value is negative 0.84 for this one. But this is symmetric. So if this z is negative 0.84, then z2 is positive 0.84. So we can use symmetry to give us our two values. So now we're going to go to our formula, and we're going to actually solve a plus or minus problem. So now we know that our z equals x minus mu over sigma. We know that our z is plus or minus 0.84. And we know our x, or we don't know our x, that's what we're trying to find. We know our mu is 120. It's from over here, remember. It was given in the problem. And we know our sigma is 15. That was given in the problem also here. So 15. So we're again going to multiply both sides. And scroll down a little bit so we have a little bit more room. So we're going to scroll down. We're going to multiply both sides by 15. Now this is a multiplication. Don't add and subtract there. So we're going to multiply by 15, and that will give us x minus 120 on the right side. And then on the left side, that's going to give us plus or minus 12.6. So we're not taking 15 plus 0.84 or 15 minus 0.84. We're saying 15 times either positive or negative 0.84. I should really say, instead of plus or minus, I should say positive and negative. So we've got positive and negative 12.6 equals x minus 120. Then we're going to add 120 to both sides. And that's the point where we do the add and the subtract. So if we do 120 plus 12.6, that gives us 132.6. And if we do 120 minus 12.6, that will give us 107.4. So they're telling us we need to go above the average by 12.6 and under the average by 12.6. Now, these are systolic blood pressures, and those are not normally measured to the tenth. They're usually measured to the whole. So we would say the middle is from, I should say the middle 60%. The middle 60% is from, it looks like about 107 for the systolic, which is the first number they give you when they give you your blood pressure. You know, like 120 over 80 is considered, in most cases, normal. This would be like the first number, and then to 133, we'll say. That's a little bit more than the middle 60% because we had to round the 133 up and the 107 down, but it's approximately 107 to 133 for that top number of your blood pressure, your systolic. Okay, so that's all our examples. So again, we had the three basic ones where we did below, we did above, we did between, and then we did a specific probability when it was just a single value. In this case, it was above, so we had to switch it to the 90% below. And then we did one that got us a middle. So those are your examples, and the first three are what are the type that you might see on the exam, or you will see on the exam. The other two, where they give us the percentage first, and then we have to go find the Z, the NASA example and the systolic blood pressure example, those are going to be on your homework for certain, but there won't be any on the exam. Okay, so how does a researcher, when they're looking at their data, how do they know whether or not they can use these methods? Remember, all these methods that we're learning are only for data that is normally distributed. So how do researchers look at that? If you were doing research at some point in the future in a class, how would you know that your data was normally distributed? Well, there's three basic things. So to test if your data is normal or at least approximately normal, you can make a histogram and see if it comes out to be bell-shaped. You get a bell-shaped curve for your histogram. If you look at it and you say, it looks pretty bell-shaped, then you could go on to the second thing, which is to calculate what we call the Pearson coefficient of skewness. It's calculated by taking 3 times the average of the data minus the median, and then dividing it by S, by the standard deviation of the sample. Remember, when something is skewed, that pulls the mean away from the median. So if you have skewed data and the median is up here, okay, if you have a median that's up here, then the skewedness would pull the mean down below that. So the skewness would pull it down. So we're going to use this Pearson coefficient to determine how far away are the mean and the median from each other. Are they significantly far away from each other? And that will help us determine. So we want this number to either be, we want it to be between, we want this to be between -1 and 1. If it goes outside of that, then we're going to say, that's too skewed. Let's not assume this data is normal or even approximately normal. And then the last thing we can do is we can look for outliers. So if we have, it says even if you have a few outliers, that can greatly affect the normality of a set. So we're going to see, does the data set have any outliers? So here is some data that we have. 18 companies, see how many days worth of inventory they have on hand. The data values collected are as follows. So this would be like how long the company could continue to function on the current inventory they have of their items that they sell. So one company could only survive 5 days on the current inventory they have if they didn't get any more inventory in. And another company, all these companies just increase, they have them in order for us, which is nice. Up to one company has enough inventory that they could continue to function normally for 158 days. So if we put this in a histogram, our histogram goes from, this first category would have, goes 4.5 to 29.5. So that would have these first two data values in it. And then 29.5 to 54.5 would have these three data values in it, and so on. Okay, so we make a graph. Now, you can see that this clearly isn't perfectly bell-shaped. If it was perfectly bell-shaped, then this, this bar and this bar would be the exact same height. And so would this bar and this bar. They'd be the exact same height. And the next ones also. But it does start low, come up to a peak, and go down. It's fairly bell-shaped. Not perfectly bell-shaped by any means, but it is fairly bell-shaped. So we'll say, okay, close enough to call it approximately normal, it looks like. So let's go on to our next data set. So our next data set, or not data set, but our next check is to check the skewness. So we're going to use this Pearson coefficient to calculate the skewness. So they're going to be nice to us and say, hey, calculations were completed, and we got the mean to be 79.5 and the median to be 77.5 and the sample standard deviation to be 40.5. So this is our S. So we got a mean of 79.5, a median of 77.5, and an S of 40.5. If you need to do that on your homework, you're welcome to, as I mentioned before, you don't have to do these by hand anymore. We've already tested on that. So if you want to use an online program, you're welcome to do that. And the one I always recommend is called Elcula. So if you go Elcula, I'm going to put in standard deviation calculator because that's the more complicated of all the things. And we would put in our data into this calculator and we could get those values. Okay, most of the homework problems, they're going to give it to you, but if they don't, you can use an online calculator, that's fine. And on the exam, I would absolutely give it to you. So we've got 5, 29, 34, 44, 45, 63, 68, 74, 81, 97. Okay, hopefully I haven't missed anything here. Okay, and then we would just, you submit this data. Oh, the other thing you have to be really careful about when you use this, Elcula wants to know if it's a population or a sample, because remember, calculating the sample standard deviation is a slightly different calculation than the population standard deviation. So make sure you click sample at the top and submit data. And we have the same numbers that were given down here. So you have your S being 40.453677, which was recorded as 40.5. And then the mean is right here. You can see that, of 79.5. And then you can click down here for other things. So I'm going to click right there. And it'll tell us that the median is 77.5. So Elcula will get you all those values if you ever need those. Whether it's in this class or another class, you can get all those data values real quickly by putting your data into the online calculator. Okay, so now back to what we were doing. We want to calculate the PC. And remember, we want to see if this PC is somewhere between -1 and 1, and if it is, it's okay. So our formula is 3 go back and refer to it. So it's 3 times x bar minus median over s. So 3 times x bar minus median over s. So in this case, that would be 3 times 79.5 minus 77.5 over 40.5. And if you calculate that out, that comes out to be about 0.148. Well, that is well between our -1 and 1. And so it's not terribly skewed. If it was above 1 or below 1, that would mean it was very skewed. Our data is not very skewed. It is skewed a little bit, but it's not terribly skewed. So we pass this test. Now, I do want to point out one thing. You notice it from the histogram. Our histogram had a slight positive skew. And that's why our skewness comes out to be slightly positive, 0.148. Okay, so we have the bulk of our data here, and remember, the tail is where our skewedness is. So bulk of the data is here, like the body of the animal, and then it tails off to the right. So it's skewed right a little bit, and so we get a Pearson coefficient of a positive number. Okay, and then finally, in order to be certain or comfortable that it is approximately normal, a researcher could check for outliers. So more calculations would need to be done. We've got a Q1 of 45, a Q3 of 98. And remember to get the inner quartile range, which is what we need for the formula. Let me write down the formula. So the formula for outliers, you're going to do Q3 plus 1.5 times the IQR. That'll give you any upper outliers. And then the lower outliers are Q1 minus 1.5 times IQR. And so we need to get this IQR first, and IQR is Q3, which is 98, minus Q1, which is 45. So that's the range between the two quartiles. I'm going to go up and show real quick where these values came from. Again, it might be given to you in the problem, but if you have to do it yourself, just a quick reminder. So these are already in order, which helps us out. Remember, the median is going to be between right in the middle of the values. So here's 6, 7, 9 values on the top row, 9 values on the bottom row. So the median is going to be right between 74 and 81. So we're going to average those, and that's where we get the 77.5. So then we're going to get the lower quartile, the Q1, and the Q3. And if we go to the lower half, which is the top row, we've got 9 numbers, so we want 4 below and 5 above. Or, I'm sorry, 4 below and 4 above, so this is your Q1. And then the same thing on the bottom, you've got 1, 2, 3, 4, 5, 1, 2, 3, 4 above. So Q3 is 98. So that's where they get the Q1 of 94 or 45 and the Q3 of 98. So that's where those numbers came from. And so our inner quartile range is the Q3 minus the Q1, which comes out to be 53. And then we're going to do our calculations. So Q3 is 98 plus 1.5 times the IQR, which is, this is our IQR. Forgot to write that down, what I was calculating. So the IQR is these two numbers subtracted, so 1.5 times 53. And so 98 plus 1.5 times 53 gets us 177.5. I just noticed that this is filled in wrong. It's calculated correctly, but it's filled in wrong. This should be a 98 right here. I'm not sure if that's on your slide or if it's not, but it should be 98 plus 1.5 times 53. You get 177.5. And then we're going to do the same thing, but with the lower. So 45 minus, so that's the Q1, 45, minus 1.5 times the interquartile range, which comes out to be negative 34.5. So do we have any values that are higher than 177.5 or lower than negative 34.5? Well, we don't have any that are lower. We know that our smallest value was 5. And we don't have any that are higher than 177. Our highest was 158. So we don't have any outliers. So none of the original data values are outside these bounds, so there's no outliers. So our conclusion is the histogram was roughly bell-shaped, check. The Pearson coefficient for skewness was small, check. And there are no outliers, check. So we can conclude that the distribution is, while not perfectly normally distributed, it is approximately normally distributed. So we can use all of those techniques that we were using before to find percentages in between values and above values and things. So that's what we have for 6.2. Now, I'm going to go ahead and continue with 6.3 for this video. And there's only one slight difference with 6.3 from what we've been doing. So in section 6.3, so you've really learned almost everything that you need to know for chapter 6. This is just a slightly different situation that we have to take into account, but everything else we do the same. And that slight difference is going to be addressed by what we call the central limit theorem. And the central limit theorem helps us to solve problems involving sample means for large samples. So you know before we were talking about x's. So we had that our z was x minus mu over sigma. But now, instead of having an x value, just a single value, like what is the likelihood that a family chosen at random has this much trash or less, or this much trash or more, we're going to have a sample. And so we're going to be saying, what's the likelihood that this sample has an average? And so instead of x's, we're going to be dealing with x bars, the average of a whole sample. And does that change things? It does. If we think about the situation where, think about people's heights. If you were walking through the grocery store, let's say, and you walked past somebody that was 6'7", you'd be like, wow, that person's tall. You might notice it. It's definitely above what's typical, but it's not going to, it's not going to be utterly surprising. You're just going to note to yourself, oh my goodness, that person is really tall. So it happens on a regular enough basis that it wouldn't be something that we would, think is just impossible. But if somebody came back and said, I randomly chose 10 people Okay, so if somebody said that, you know, they had an X of 6'7" that's one thing. But if somebody came back and said, I took a sample of 10 people, and we won't even go as high as 6'7", but if they came back and said, I took just a random sample of 10 people, and I got an average height of 6'2", you would be like, wait a minute, where are you getting these people from? Because the average person is not 6'2". The average person is probably more around 5'6", 5'5". So where did you find these people? Were you going into a basketball locker room? Were you at a football clinic? Where were you at that you were finding these exceptionally random 10 tall people? And so that demonstrates what we're going to be doing in this section. We have to alter things a little bit, because an individual value being above the mean by a certain amount is a lot more likely to happen than to have an entire sample have their average above or below the mean by very much. Because when we do that sample, you get some that are below, some that are above, and we expect our average to be somewhere close to the mean, to the mu of the population. And so we have to make a slight adjustment when we do our calculations. It's not terribly difficult. You just have to recognize that when the problem asks for, when the problem says that it's a sample instead of an individual, you have to use this adjustment. So let's get into it. So when you select a sample from a population and you're calculating a sample mean, that itself is a random experiment. So the probability distribution of the sample mean is called the sampling distribution of sample means. So we have a distribution of the means of samples instead of just individual people. The sampling error is the difference between the measurement that you get in your sample and the population measurement. So what did you get for a mean for your sample? What did you get for your mean, or what's the mean of the population? And you really should, the expected value is that your sample will be the same as the population. Because again, we're taking a sample, so if your sample is, you know, decent sized, you would expect that you would get some above and some below, and it would come out to be pretty close to what the population was. But the standard, and so that standard error is going to be smaller when you're talking about sample means than with just individuals. And so, not to get into too much of the theory here, but as the sample size increases, okay, you want to get your sample size, you know, instead of 10, you have a sample of 20 or a sample of 100. As you get closer and closer, or larger and larger with that sample size, you would expect the X bar to get closer and closer and closer to whatever the mu is. Your sample average to get close to what the mu is. And because of that, it changes the standard deviation. So the standard deviation becomes smaller. As you get a larger sample size, the standard deviation is less spread out. And in fact, it's less spread out by this amount. So the standard deviation of the sample means, so the standard deviation of the X bars, is actually whatever the standard deviation was before divided by the size of the sample. And again, if you take and make this number right here larger and larger and larger, that's going to make this whole thing get smaller because you're going to be dividing by a bigger number. So as your n gets bigger and bigger and bigger, this whole thing is going to get smaller and smaller and smaller and start to look like the actual sigma was before. Again, that's a lot of theory. You don't have to worry about that in practice so much. Just understand that we have to adjust for that sample size. And so what we just talked about, that last fact of the sampling distribution of the sample means, that gives us what we call the central limit theorem. And all it does in practice for what we're doing is it changes our formula for z. So remember, when you're talking about an individual, you're using z equals like just an individual data value. You're using x minus mu over sigma. When you're doing it for a sample, when it says what's the probability or the likelihood that a sample, you're going to use z equals, there's actually something missing here. This should have a bar on top of it. So it's going to be x bar minus mu over sigma divided by the square root of n. So you have to add on the bottom here. Notice the only real difference is instead of an x, we're using an x bar, and instead of a sigma, we're using a sigma over square root of n. We're adjusting for what we said on that prior slide. We're using that sigma over square root of n now. And then it says all our other calculation methods from 6.2 stay the same, 6.1 and 6.2. A sample doesn't have to be very large for the sampling distribution to be approximately normal. If the population is normally distributed, the sampling distribution is definitely going to be normally distributed. But even if the population wasn't normally distributed, if you get a sample size of 30 or more, then the sampling distribution, this sampling, the averages of the sample means, the samples from the sample means, is going to be approximately normally distributed. And as we said, the larger the sample, the better, basically. Okay, so let's see what this means. And this is our last example. Again, everything is the same on these except for we're going to change our formula. Gosh, the formula is wrong here too. Please put a bar over your x on your notes. Okay, that's supposed to be x with a bar over it, not just a plain x. Okay, so this is what these problems sound like. On average, a U.S. adult skips breakfast 50 times a year. Assume the standard deviation is 4. So this 50, that's our mu. Our standard deviation, our sigma, is 4. And it says for a random sample of 36 adults, we're supposed to find the probability that the sample mean is between 48 and 51. So I'm going to draw a graph the same. So in the middle, we've got 50. That was our average. We want to find the probability that we're between 48 and, see if I make my line a little straighter there, that we're between 48 and 51. Okay, so between 48 and 51. So we want to know the probability that we're between those two values. Okay. Now, how do we know this is a central limit theorem problem and that we need to use this formula instead of the other formula? Well, because it says a random sample of 36 adults. Find the probability that it's between these. It doesn't say what's the probability that two individuals are between this. It says 36 adults in a sample. So that's our n. So we have an n to use in this formula. With the other problems, we didn't have an n. I mean, we did have an n. I mean, technically, we had an n. Let me write down our old formula. So in our old formula, or let's write down our current formula and we'll compare it. So if we were doing this with just an individual, we have an individual, which means the average for that individual would just be x because it's just them. They're their own average. And then the sample size would just be 1. So sigma divided by 1 would just be sigma. So it really is the same formula. It's just that when you're talking about an individual, that individual's average is just itself. And the n is 1, so I don't have to really do sigma divided by 1 because that's just sigma. So it really is the same formula, but we used the simplified version before. So now we know that we're going to use the central limit theorem formula because we have an n. If we have a sample, we're doing central limit theorem. So because this is a between, I'm going to have to find two different values. So do our Z2, which is the 51. I always like to do the bigger one first. So we have 51 minus 50 over sigma, which is 4, over the square root of n, which is 36. Again, I'm plugging into this formula. So x bar is 51 minus 50, which is the mu, over 4, which is the sigma, the standard deviation, over the sample size, which is 36. So in this case, that gets us 1 over 4 over 6. Be really careful when you put this on your calculator, and I would really recommend you try it right now. This number, the calculator needs to know that that and this are the top and bottom of the fraction. So you could either enter it all the way in your calculator by doing parentheses 51 minus 50 parentheses divided by parentheses 4 over square root of 36 parentheses. What I like to do is at least calculate the top on its own and do 1 divided by parentheses 4 over square root of 36. There's various ways to do this, but you have to get it into your calculator, right? You should get 1.5 when you work this out. Another way to do that, okay, so here's the calculator. So one way is to just put it in from the beginning to the end, making sure that you put parentheses around your top and then around your bottom. So 51 minus 50 divided by parentheses 4 divided by square root 36. And then there we go. And that gets us our 1.5. The other thing you can do is you could do just the bottom. So you could do 4 divided by square root 36 and get that as an answer. And then you know 51 minus 50 is 1, so you could just do 1 divided by answer. I tend to do that because I don't like putting it in big long strings. I'm always afraid I'm going to miss something. So I feel like I'm more accurate if I do the little bottom part, get that answer, and then do 1 divided by that bottom part. And you should still get the same answer, so 1.5. Okay? So now we're going to do the other one. Let me pop the calculator open and we'll do that one too. So we're now going to do the other value, which is Z1, and that's for the lower value, which is the 48. So 48 minus 50 divided by 4 over square root of 36, which equals negative 2 over 4 over 6. This one's convenient because 36 is a perfect square, but often it's not. So you have to just leave that square root in there. And so if we pull that up, we get if you do it in the long way, it'd be 48 minus 50, if you do it all at once, not really the long way, just if you do it all at once, divided by 4 over square root of 36. You should get negative 3. Or if you'd like to do it the way that I prefer, I just do the 4 divided by square root of 36. I get that answer. And then I just look at the top. I see, oh, that's negative 2 because that's an easy calculation. So I do negative 2 divided by the answer. And you still get negative 3. So either way, you should get a negative 3. And you might want to practice that just to make sure you aren't frustrated on your homework. Okay, so we get negative 3. And so those are our z values. Now, because it's a between, I'm going to go to the chart for both of those and then subtract. So the biggest thing with this is not different than the other ones we've done that were betweens. The only difference here is we have to remember, because it's a sample, okay, because it's a sample, we have to use the central limit theorem instead of the regular formula that we were using before, or the formula for the individual that we were using before. Okay, so let's back this up. So our first value that we wanted to look up was 1.5. So 1.50 is right here. 1.50 is 0.9332. And then if we look up -3, it's going to be on the other page. So -3.0 is -3.0 would just be right here. It'd be this 0.0013. And then if we subtract those, so we're going to take 0.9332 and subtract 0.0013, we're going to get 0.9319. So there's a 93.19% probability that the sample average for the number for the average of the sample is going to be somewhere between 48 and 51. 93% of the time when you take a sample of 36 adults, you're going to get between 48 and 51. All right, so that's our last example. Best of luck on your Chapter 6 homework, and we will see you back for Chapter 7. We only have Chapter 7 and Chapter 8 and part of Chapter 9 left after this. Unless you're in my summer class, we haven't done Chapter 10 yet, or my mini class. But for the regular session classes, we only have Chapter 7, Chapter 8, and part of Chapter 9. There was one other thing I wanted to point out, just real briefly before we call it a day. We've got, when we're looking at Chapter 6, and you look at your formulas, remember, you don't have to memorize any of these formulas. There's the formula for Z. We don't really need to know how to find this. You don't have to calculate that. And then here's your formula for the central limit theorem. So you've got your formula for your regular Z when you just are talking about an individual, and you've got your one for central limit where we've got an N. So we have a sample, and so we are going to be using the sample size in the formula to accommodate for that sample size. So we've got to put that N into the formula to accommodate that it's a sample and not just an individual. Okay, but those are both on your formula sheet. You don't have to memorize them. All right, have a great rest of your day, and